Let's go ahead and talk about refrigerators and heat pumps. So, a refrigerator is a device that transfers heat from a low temperature source to a high temperature medium, right? If you remember, what we just went over earlier is that if you have a heat engine goes ahead and takes heat from a hot source, rejects heat to a low source, and then produces a net amount of work. A refrigerator absorbs, there's a certain amount of work in that results in heat moving away from the cold source to the hot source. So basically what you're doing is that you're causing heat to flow in a direction that is opposite in nature, right? In nature, you have heat that usually flows from a hot source, from a hot temperature to a low temperature. But in this case, you're making heat flow the opposite direction by putting work into the system. Now, what does a refrigerator system look like, right? We went ahead and we analyzed earlier what a heat engine looks like, what is actually inside this heat engine. Now let's look at what's inside this refrigerator. Just to make the comparison, I'll go ahead and I will draw at least a bit smaller diagram here of what our heat engine looked like. So if you remember, we had in our heat engine liquid water goes into a pump, gets pushed up to a higher pressure. So I have high pressure liquid water. So I have work going into the pump. I have heat being absorbed in the boiler. We would have high pressure steam coming out of the boiler with Q in, and then I have a certain amount of work coming out of my turbine due to high pressure steam going in, low pressure steam coming out. And then my steam goes into a condenser, and I reject heat through the condenser to convert the liquid water back into, to convert this low pressure steam back into liquid water. Now, if you think about it, a boiler is an evaporator, right? It's making the water evaporate. So if I take my boiler or my evaporator, I make it into a condenser. I take my condenser, I make it into an evaporator. I take my turbine, I turn it into a compressor. And I take my my pump, and I make it the expansion valve. And instead of the fluid flowing this way in the heat engine, I make it flow the opposite way in the refrigerator and replace the water with refrigerant. Then I have a refrigerator. Now, I'm going to go ahead and explain how a refrigeration process works. So, refrigeration process uses refrigerant where the refrigerant has saturation properties that allows me to absorb heat in a cold space and reject heat to a hot space. So here's how it works. Let's say, for example, I start here at state 1. I have my refrigerant in vapor form. It's in either a saturated vapor or a slightly superheated vapor form at a really cold temperature. Let's say, for example, negative 20 Celsius, right? You're probably thinking, how can anything be a vapor at negative 20 Celsius? Well, that's what the advantage of refrigerant is that it phase changes at pretty low temperatures and pressures, right? So here I have my pressure at 120 kPa, my temperature at negative 20. My compressor increases the pressure to a high value, in this case 800 kPa, and my temperature is at 600 C. Then it goes through a condenser. Now, it goes into the condenser and rejects heat to the environment, converts it back into a liquid coming out, again, at a high temperature, right, 30 degrees. Then it goes into an expansion valve. If you remember back in chapter 5, we studied expansion valves that are isenthalpic devices, right? We went ahead, we did a first law analysis on it, and the first law analysis resulted in the fact that the enthalpy going into the expansion valve equals the enthalpy coming out of the expansion valve. Why is that a big deal? Because what that does basically is that it drops the pressure significantly, in this case from 800 down to 120, and what happens is the temperature also drops, and it comes out as a saturated liquid vapor mixture with a very low temperature, ready to go into the evaporator and absorb heat. So let's think about this in terms of something that you might be familiar with. So let's say I have an air conditioner, right? My room is cold. I go to Walmart. I buy an AC. I install my AC in my dorm or my room. So let's say that this is the window. The AC is installed. We'll call this inside. We'll call this outside. Now, we'll say that here is the evaporator, and outside is the condenser. So, what I'm trying to do is make the inside of the room cold and the outside of the room is hot. And I'm trying to take heat and move it from inside the room to outside, right? In order to keep the room cool. I want to make my room cool because it's hot out. So here's how it works. Coming out of the compressor, I have my refrigerant is really hot. It's at 60 C at 800 kPa, right? The condenser is out here. What happens is that the outside part of the air conditioner takes air as a fan, takes it inside the system here, blows the air over the condenser in order to dissipate the heat from the refrigerant to the outside. Q reject, QH. I'm rejecting my heat to the environment by using the air outside to exchange heat with the refrigerant so that the air outside absorbs the heat from the refrigerant, turning the refrigerant from a superheated vapor here to a liquid here. And the way to do it is that this pressure has to be at such a value that the corresponding saturation pressure is hotter than the outside air. Right? So I have TH, this is the temperature outside. In this case, it's T ambient. So my outside temperature, let's say, is, I don't know, let's say it's 40, let's say it's 100 degrees Fahrenheit outside. That means that I need to pick the pressure of the refrigerant such that as it's condensing, it condenses at a saturated state, right? It's turning from gas into liquid. As it does that, I need to make sure that the phase change temperature, that saturation temperature, is higher than the outside temperature of the air. So let's say that the saturation temperature is 150 degrees Fahrenheit and the outside temperature is 100 degrees Fahrenheit. I'm going to reject heat to the outside, where that heat rejection is going to cause that refrigerant to turn into a liquid. So now I've rejected the heat outside. My liquid is still at the same pressure, but it's at a higher temperature. Now what I want to do is drop the temperature of that refrigerant significantly. I just want to drop it. So I'm going to drop the pressure down to a very low pressure so that my refrigerant's super cold. In this case, it's negative 25 degrees. So now that refrigerant is going through the evaporator coils, which is on the inside of the room. So now I take inside air, it goes into the fan, that inside air comes out of the fan, and as it goes in and out of the AC by a fan blowing it over the evaporator coils, the refrigerant now is absorbing the heat from the room, where the heat transfer from the room air to the refrigerant is causing the refrigerant to evaporate. Again, it's all done in a way so that I choose my pressure of the evaporator so that the saturation temperature is much lower than the room temperature. Right? The room temperature is going to be basically TL, the temperature of the cold source, or of the cold medium, the low temperature medium. So I have to pick the saturation pressure so that saturation temperature is lower than the room temperature so that I absorb heat from inside the room. And then as it comes out of the evaporator, it's going to be probably a superheated vapor or maybe a saturated vapor. And then that's going to a compressor in order to push the pressure back up to the operating pressure of the condenser, such that the saturation temperature at the condenser is higher than the outside air, so I can reject heat back to the outside air. And that's how the process works. And that's why refrigerants work well, because their saturation properties lends itself to be able to be a good working fluid for this type of cycle. All right. So how do you measure the performance, or quote unquote, the efficiency of refrigeration cycle. Well, we don't use efficiencies. It's called coefficient of performance. And again, it's just same basic definition as the efficiency, where it is the desired output over the required input. Now, why is it called a coefficient of performance and not an efficiency? Because you can have values greater than 1. It's a coefficient. It's not a percentage, right? So if I say my refrigeration system operates at a coefficient of performance of 3, that's not 300%. That's a coefficient of performance of 3. This is not a percentage. The coefficient of performance is not a percentage. It is not an efficiency. It is a coefficient. So the definition is what you want over what you have to put in. So the coefficient performance of a refrigerator, what do I want? What I'm trying to do is, if this is my cold space, the inside of my room that I'm trying to air condition, or the inside of a refrigerator, what you want is to remove heat from that refrigerator. So it's actually the heat you're removing from the cold space. A lot of people think that the point of a refrigerator is to reject heat, right? So you want actually the heat that you're rejecting. No, it is the heat you are absorbing. That is the desired output for a refrigerator, is the heat that you are removing from the cold space. And then a required input is the work in, right? So again, if you want to expand this, work in can be quantified as the heat rejected minus the heat absorbed. And that could be basically the coefficient performance, right? And you can actually algebraically reduce this down to 1 over the quantity QH over QL minus 1. That is for a refrigerator. Now, we're also going to look at heat pumps. Heat pumps, hear me out, heat pumps and refrigerators are the same thing. They are the same thing. They operate on the same cycle, and they are both what are called reversed heat engines. But the only difference, the biggest difference, is that the objective of the heat pump is to maintain a heated space at a certain temperature. So what you want, your desired output, is this QH, not the QL. The QL is desired output for a refrigerator. QH is desired output for a heat pump. So if you define your coefficient of performance for a heat pump, it would be the desired output, QH, over the required input, work in. And the coefficient of performance for the heat pump is equal to that of the refrigerator plus 1. Okay, so this brings us to the second statement in this chapter, called the Clausius Statement. The Clausius Statement says, it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a higher temperature body. Basically what this is saying is, I can't make heat move from cold to hot without putting work into it. That is the whole premise behind the Clausius Statement. So it's basically saying that between a high temperature reservoir and a low temperature reservoir, I cannot convert all heat into a net amount of work. This is impossible. And I cannot have a refrigeration system that allows me to move heat from a low temperature to a high temperature. I need to have work in. Otherwise, it is impossible to have. It is impossible for it to occur. All right, let's try an example problem here. A household refrigerator with a coefficient performance of 1.2 removes heat from a refrigerated space at a rate of 60 kilojoules per minute. So let's go ahead and draw our system. So I have here a kitchen, right? That's when we're rejecting heat to from the refrigerator. Here is the cool space, right? The space at which I'm trying to keep cool in the refrigerator. Here's my refrigeration system. I'm absorbing work to make heat move from the cold space to the warm space. And it's asking me to determine the electrical power consumption of the refrigerator, right? So that would be the work in. The work into the refrigerator is the amount of work that the compressor is consuming, or the amount of electrical work that the refrigerator is consuming. And it's asking me to find the rate of heat transfer to the kitchen air, which is QH. How much heat am I rejecting to the kitchen air in order to keep the cool space maintained at that temperature, at a specific temperature? So it's telling me that it removes heat from the refrigerated space at a rate of 60 kilojoules per minute. So that would be QL. The amount of heat I'm removing from the refrigerated space is QL. So that would be 60 kilojoules per minute. And basically, I need to find that out. So here, I have to find out what the QH and work in is. If I look at the coefficient performance for a refrigerator, it is quantified as the heat being removed from the refrigerated space divided by the net work being consumed. So it's telling me that it's 1.2 is the coefficient performance. QL I'm given as 60 kilojoules per minute. And work in would be my only unknown. If I go ahead and solve for work in, and I put it into kilowatts, I can get that this refrigerator, based on that coefficient performance, is consuming 0.83 kilowatts of power. That would be for part A. And then part B is asking for the amount of heat being rejected to the refrigerated space. So if I go ahead and do a first law analysis on the whole refrigeration cycle itself, I get energy in. If I assume that this is all operating at steady state, I can go ahead and do a first law analysis where E in minus E out equals delta E system. Delta E system goes to 0 because it's steady state, so I'm left with all energy in is equal to all energy out. So if I do a first law analysis around the whole refrigeration cycle itself, I get that work in and Q in, so work in plus Q in is equal to all energy out, which is just QH. That's the only energy leaving the whole cycle. I have QL. It was given to me. I have work in, and I can compute QH. Just add QL and W in together, and I get that this refrigeration system, this household refrigerator, is rejecting 1.83 kilowatts of heat to the kitchen air.